discussing about different distributions, and we have taken up binomial distribution and tried to understand that with some sample problems, and we also looked into the working formula for that. So binomial distribution and Poisson distribution are both depends on the discrete variable, okay? And in binomial distribution you basically will have two kind of results: pass, fail, yes, no, head, tail. Everything can come under something which is called as the binomial distribution. So what we're going to do today is we're going to talk about Poisson's distribution. Okay, so just going to do it in short. So we're going to talk about Poisson's distribution. So this understanding of this distribution is not that difficult, because if you understand a bit of statistics, these things should not be very complicated. Okay, so this Poisson distribution again describes discrete data. Okay, so I've just written that as a point, but then in general when you write down an explanation for this, you can just take it. Okay, that is situations where the random variable can take integer values. Okay, random variable can take integer values. So this is a point. And then if we just talk about the integer values example, what kind of problem can be solved, we can talk about number of cars, okay, at a toll booth. So how many cars will pass at a given point of time will actually is more or less discrete in nature. It's not something which is constant, so you can talk about that. Okay, or basically talk about number of patients in a hospital keeps on varying from time to time, so you cannot take these kind of examples. Okay, so just as in binomial distribution we have got mean as np and variance as root over of npq, we similarly have a mean here. So basically it means that number of occurrence, we're going to look into a problem in some interval of time. Okay, in some interval of time. Okay, so that is mean. And standard deviation, okay, is nothing but the root of mean. Okay, which is common. If you know the mean, you can actually find out the standard deviation. Okay, should not be complicated. So in general when we talk about this mean, it is usually denoted by lambda, and standard deviation is always root of mean. Okay, so this is nothing but can be taken as root of lambda. Okay, so that's Poisson distribution. And then there should be a distribution function. Okay, so if we're basically considering x, okay, and x might be a Poisson random variable, so this is basically called a Poisson random variable. Okay, so this is all about finding out a result given on some parameters. Okay, so if we are considering this x as a random variable, this Poisson distribution, just like binomial distribution, will have a form, and this is actually given as lambda to the power x into e to the power minus lambda divided by factorial x. There is a minus there. So this is the Poisson distribution form. Okay, and if you're basically considering some example to find out using this, one more example that I can consider is typos in a book. Typos in a book or in a page, whatever. Okay, so this is a number which is quite high, and in no way it can be actually talked about under binomial distribution. Okay, is there a typo? Yes or no? Yes, it can be a binomial distribution, but how many typos, that will actually depend on Poisson distribution. Okay, so based on this idea, probably we can just take one example. Okay, let's try to do a numerical problem here. Okay, so just take one problem here. Okay, so let's take an example. Let's say the mean is given to be 1.5. Okay, so for a certain result the mean is already provided to you, so that means the lambda value is with you. Okay, what we are going to do now is just going to frame the question. Suppose 100 pages are randomly selected. What is the probability that there are no typos. So I hope you understand what is typo. It means there are typing errors, okay? And if the 100 pages randomly selected, what is the probability that there won't be any kind of errors in typing, okay? So that is what is the question is all about. So what are the parameters that I have? It's given that x is equal to 0. That means no typos, okay? And then this mean is given to be 1.5, okay? So if we have that, we can just simply use the distribution formula and we can take this. P0 is equal to 1.5 to the power 0, okay, into E, okay. So you can take it to be 2.7 minus 1.5. You will basically have this E value in your calculator. You can use it directly, divided by factorial 0, okay. So if you can, all of you can recall, factorial 0 is nothing but 1. And if you do this calculation, you should get the result to be approximately 0.2231, okay. So if you just want to find out it in terms of percentage, you can simply say that there are 22.31% chance that this 100 pages which is selected at random won't have any kind of typographical error, okay. So that actually mainly depends on mean. So this value of lambda needs to be provided to you, okay. And I think this a point where I should say that this Poisson distribution might actually stand to normal distribution, okay. So when n, I'll give you this basic idea here, n is greater than 20. So whenever you are going to draw a graph, okay, between let's say two parameters, okay, what is the probability on one side, or the distribution, okay, probability distribution on one side, and on one side the parameter, let's this x 0 1 2 3 4, these are the parameters, okay. And then you can talk about the probability. So the question might be probability that there are 10 typos, so x would be 10, and then 20 typos, x would be 20, and then you can find out the probability, and then you can actually plot a graph, okay, between this x and this probability distribution, and then you will get a pattern here, okay. So what happens is, if this n is very large, that means the number of observation that we are talking about is very large, this behavior of this particular distribution, okay, the graph or the similarity, this Poisson basically will tend to binomial. It will basically tend towards binomial distribution. Okay, so n greater than 20, Poisson will actually tend to binomial distribution, okay. Now if this mean, binomial distribution mean is np, n into p, okay, total number of observation into the probability of success. If this is greater than 5, okay, and nq, that means n into, let's write down p minus 1, is also greater than 5, okay, then this binomial distribution will actually tend to normal distribution now, okay. So normal is something which is more or less continuous in nature, okay. So probably if I just want to draw a graph for Poisson distribution, let's say, okay, let's take it here. If I want to draw a graph for Poisson distribution, probably I can do it this way, okay. Okay, this is a Poisson distribution, let's say I want to draw it, and will draw it now. And then this is something which is more or less a normal distribution. So normal distribution is continuous, okay. So if you remember, okay, if you remember, this normal distribution is actually a continuous variable, Poisson is discrete variable. So if you are having n number of observation, many observation, we're basically going to get more and more points. So the distribution will become more and more continuous in nature, okay. So this is what is the meaning here, okay. So what I'm going to do is, I'm probably going to just show you this here. Let's say I want to actually draw the probability distribution curve, okay. So I'll just take up this, and I will take this px along this direction, okay, and then x along this direction. Okay, and if it's discrete in nature, okay, probably you'll get a value here for certain value of x, maybe you can get a value here for certain value of x, maybe it's here. Okay, so we can just drop a line. Okay, we can drop a line rather, and this is how the distribution will look like. But imagine between this point and this point you are having so many observations, so these lines will come very close to each other, and this will actually give you a feel of a continuous nature. Okay, so if that happens, and then what happens is that the graph will actually look like a normal distribution curve. Okay, so this is px and this is x. Okay, and if you all have seen a normal distribution curve, which is also called a bell-shaped curve, okay, this will be something like this. This is normal. Okay, and maybe this one can be considered to be discrete, so it's, let's say we can talk about binomial also, because binomial also discrete. So this is binomial. So if these conditions are fulfilled, the distribution graph will actually look like this. What does it mean? It means that there are so many points here which are very close to each other. There are n number of observations being observed. Okay, so if there are so many observations, you are going to get a distribution which will be more or less looking like a bell-shaped curve. This is the normal distribution. So we're going to discuss normal distribution separately, but then the condition under which Poisson tends to binomial and binomial distribution tends to Poisson distribution is important. Okay? But we can see that there are some basic differences between binomial distribution and Poisson distribution. So let's just write down the difference between the two. Okay, so maybe on one side I can take binomial. Okay, on the other side I can just pick up Poisson. So let's just try to write down some points of differences between the two. Okay, so the first point, let me just write down the points on binomial side, and then we can actually shift to the other side. So number one, okay, only two possible outcomes. Okay, so basically you can either have, in general, if we say, you can either have success, okay, or we can actually have failure. These are the only two possible outcomes right here, okay, in binomial distribution. Number two, probability of repeated, okay, repeated number of trials are studied. So example, let's say tossing of a coin. You have a coin, you toss it 10 times. How many times you are going to get head? How many times you are going to get tail? Okay, and that is what is the repeated number of trial means. Repeated number of trial plays a very important role in statistics. Okay, and when we are actually defining a sample space. Okay, mean is basically equal to n into p. Okay, I'm not defining the term, I think you already know it. Okay, and this will always be greater than the variance. Okay, variance. Okay, and okay, so variance, okay, and variance, you know, is nothing but npq. Okay, so I hope you understand this, because you know n into p, probability of success, and q is 1 minus probability of success. So you're going to get a value of q which is also less than 1. So multiply a value with less than 1, you're obviously going to get a value which is less. So mean will always be greater than variance. Okay, you can put up the values and check. Okay, and then there is a constant probability of success here. Constant probability of success. Let's look into the other end, and then let's try to understand what do you mean by, what are the factors in Poisson distribution. Can be, okay, so number one, can be unlimited, okay, unlimited number of possible outcomes, number of possible outcomes. Okay, and on the next point. Okay, so the count of independent events, okay, independent events occur randomly. So if you just look into the mean differential factor, okay, with a given period of time, with a given period of time. So you see this, let's say example, the typo in a book, okay, you are considering 100 pages, and then the next 100 pages, and then the next 100 pages. All of them are independent of each other. So in the first 100 page, maybe the probability of getting no typos would be different from the next 100 page, okay. So you have to just see into this, but then this will actually depend on how large the book is. If the sample space is small, probably that change is not being observed, okay. So typos in a large book. Next is mean, and mean and variance are equal in this particular case, okay. Standard deviation is root lambda, so variance is lambda, so mean and variance are equal both the cases, okay. And then the chances of success is less, actually, infinite chance of success. So the chances of success in case of binomial distribution is more, okay, but then in case of Poisson distribution the chances of success are less, okay. So you can think about the typo in a book. It's not that every time you're going to get the same kind of result, okay. That's important. Okay, so the third distribution is actually a constant distribution, and not something which is dealing with discrete data, okay, and that is exponential distribution. Exponential distribution, okay. So let's just look into the points, some important points, okay. So this basically is used to model, okay, in general these are actually used in industries and all. Suppose you are manufacturing some batteries or something which actually keeps on having a lot of manufacturing defect, okay, and in order to understand that how is this defect being distributed over a period of time, we can actually consider these kind of models. So that is exponential distribution, okay. So it is the model, the behavior of units, okay, that have constant failure. Depends from problem to problem what kind of model we use, okay. So we can actually use it in analyzing the reliability and availability, okay, of electronic system. If you're manufacturing a product at a lower cost, the chances of it failing might be more, okay, because of the equipment that are being used, okay. So for analyzing these kind of data, okay, statistical information, we actually use this distribution. So the examples might be the time to fail, let's say time to failure of electronic component, okay, that might be one, okay. The time for radioactive nuclear decay, okay, the time for radioactive nuclear decay. So if you just remember your nuclear physics, okay, radioactive decay, n is equal to n naught e to the power minus lambda t. That is actually nothing but an exponential distribution, okay. So that is a good example. The distance photon, let me take physics example, travels, okay, a medium, maybe that can be also an example, okay, before collision with dust particle. That is also something which is not linear in nature, that is more or less again exponential in nature, okay. One more important point is this is interesting, okay, exponential distribution is memoryless, okay. So what do you mean by memoryless? It simply means that basically whatever is the let's say an electronic component, whatever is the remaining life is independent of its current age. So let's say you have got an electronic equipment which is running for, let's say, the last 5 years, okay. So that means its age is 5 years. Doesn't mean that it will last for the next 5 years, okay. Probably it will last a little lesser or might be a bit longer, you never know, okay. So this is what is called memoryless is all about, okay. So in general we can say the remaining life of component is independent, okay, of current age. So this is what is exponential distribution, is memoryless, okay. Why we call it as memoryless, okay. So if you just want to measure the central tendency and dispersion, probably I'll take up this mean, okay, is usually represented as mu, okay. And mu actually in other cases also we can represent it as mu, but we have not written it. It is 1 divided by lambda, okay. So I'll just take this, okay. But what exactly do I mean by mean? And let me just take the pen here. So this mean is usually denoted by mu, and this is 1 divided by lambda, okay. So if mean is this, you can also find out what is the standard deviation, okay. But you know, interestingly, in this particular case, this mean is equal to standard deviation. Standard deviation, okay. And standard deviation is usually denoted as sigma, okay. And what does this mean exactly mean, okay? Mean time to failure. It means mean time to failure. Okay, so this is interesting. And then this lambda is basically called the threshold parameter. Threshold parameter. Okay. So please keep a note of this, okay. So this is actually nothing but threshold, because after this particular parameter or after this particular event happens, the failure starts, okay. So maybe we can write down this: after which failure starts. Failure starts. Okay, we have to just take care of this. So if we just write down the distribution here, so if we consider x to be the failure, okay, let x be the failure. That's after a time t, this is the failure, okay. Then what we can do is, this distribution can be written as, it is actually a function of x and lambda, okay, and this will be nothing but lambda e to the power minus lambda x, okay. Just before that, I'll just write down this: for radioactive decay, n is equal to n naught e to the power minus lambda t. How much atom remains after a time interval of t if the decay constant is lambda? So n naught is the original number of atoms, and this is the atom after a time t, okay. So these kind of distributions actually comes under the what we call as the exponential distribution. So you can see that this x is failure here and this x is here, okay. In this particular case, this is the time t, okay. So it depends on what kind of problem you are considering, okay, and what you consider as a failure, but this is a general statement here. And this x will be greater than or equal to 0, okay, and this will be 0 if x is less than 0. So this x value has to be positive, okay, it has to move only in the positive direction, not in the negative direction, okay, and that is the distribution that is there. Okay. So what we will do is, we will stop here with the exponential distribution.